And thanks for the organizer for organizing this symposium, this COSI. So I'm a postdoc at the University of Lausanne, and with this talk, we're going to talk about the relationship between population genetics at the within species level and phylogenetic at the between species levels. So usually, evolutionary biologists, they study evolution at different time scales. So either at the phylogenetic scales between species, where you look at gene trees, species trees, or at the population scales, where you look at variations between individuals and between populations within the same species. And the questions we have here is that, is there a bridge between those two, and how can we do it? And so we're going to divide that in two, and the first question is, first, can we estimate the fitness effect of any mutations at the phenotypic scales first, which has been shown before? And then how is that selection predictive of what is happening currently in a given population? So let's start with the first one. So for that, it's really important to realize that the DNA alignment between species is made of substitution that occurred along the tree. And the substitution, if we actually zoom in, there were mutations that occurred in one individual that reached fixation in the populations. Meaning that in terms of mathematics, what we can write is the substitution rate as a function of mutation rate and the probability of fixations, which is itself a function of selection. So with that in mind, we can actually write mathematical models. So the left-hand side here, this is for the mathematician in the room. So this is how substitution rate is modeled as a function of mutation and selection for the different amino acids. And for the, for the people that are more used to pipelines, and this is what input-output is. So you have an MSA as an input and a gene tree, and what you get as an output is a fitness profile across the different sites. So there's a plot twist here. This is not deep learning. This is a basic Bayesian framework that allow you to get these fitness profiles. And so what are those exactly fitness profiles? So just to look a bit at what they are, let's assume that we are at a P. So we have a species that have a P that is fixed. And this is the highest fitness. And if you move around, any mutation that is going at any other amino acids, let's say N or M here, this is really bad. This is really not fit and purified away. Well, if you're going from P to T, this is not that bad. And just because of genetic drift, it's actually possible that this mutation reach fixation in your populations, although it's deleterious. And then on the other round, then you can have, if you're going from low fitness to high fitness, you have a beneficial mutation that is more likely to reach fixations. So this is how you can read this fitness profile and the difference in the mutations between this fitness. And if you now look at the exomes across humans and you look at all the mutations possible away from these exomes, this is what it typically looks like. So most of the mutations you're going to generate are deleterious. So using the vocabulary that we've seen before, they are pathogenic with a negative selection coefficients. A few of them are nearly neutral, so benign. And only a few percent, 1 or 2, is actually beneficial, so going to a higher fitness. And we've looked at statistically, effectively, the deleterious are associated to pathogenic, the nearly neutral associated to benign. And the beneficial, they actually have an increased substitution rate compared to neutral, so they are actually fixing at a higher rate than the neutral one. So with that in mind, can we now contrast what the predictions we've made using phylogenetics to what we are seeing at the population genetic scale? And so for that, we're going to use another models at the population genetic scales. And this is what we typically use is a site frequency spectrum here shown for the synonymous mutations that we here consider neutral. And here non-synonymous mutations. In that case, we just look at the deleterious ones. And what we're seeing is that the high frequency variant in your populations are actually purified away. You don't see them as much as the synonymous mutations. So that indeed, for those mutations that you've predicted as deleterious, this seems to be under purifying selections right now in humans. And you can actually build a model. And there's a second plot twist here. It's still not deep learning. This is just maximum likelihood. And the parameters are just, how much of the mutations are deleterious, how much are nearly neutral, and how much are beneficials. And this is our parameters that are estimated just given these two side frequency spectrum, the non-synonymous and the synonymous. And here, for this example, by feeding all the deleterious mutations that we've predicted, we recover that around 90% of them were actually true positive, very correctly estimated, while around 10% were actually false positive, meaning that we predicted them as deleterious, while apparently right now in humans, they seem to be either nearly neutral or beneficials. So if we do that across the different categories that we have, what we are seeing is that for the one we predicted as deleterious, they are effectively recovered as deleterious. For the one that we predicted as nearly neutral, they are also recovered more frequently as nearly neutrals. And also for the beneficial ones, they are actively under positive selections right now in humans, meaning that here we have a good agreement between what is estimated across mammals and what we are seeing right now in populations. And so that's basically what I want to get as take-home messages, is that we can use phylogenetic models that are models as function of selections and fitness to predict what is happening right now in populations. So here I was showing only in humans, but we had several data sets that recovered basically the same IDs. And what's important also is that the fitness landscape seems to be stable enough across mammals so that the estimations that we have done at the mammalian scale is actually predictive of what is happening right now. So this is really an information that, and for that, we have the sensitivity and the recall that is associated to it. And so with that, I'm happy to take, thank you for your attention and happy to take any questions.
Are you just looking at coding variants?
Yes, yes. So we're looking at coding variants because we need to contrast to neutral expectations. So in that case, we use the synonymous ones. So that's the first reason. That's also the reason why we are looking actually at mammals, because in mammals, we know that synonymous are more neutral. Like, let's say in Drosophila, we know it's less of the case. While in mammals, like it has been shown that synonymous is more or less neutral. And also because this model have been built at the protein coding levels. Yes.
So what's under positive selection?
What's in the positive selection? Yeah, okay. Thanks a lot for this one. So in the positive selection side, what's happening is that here, what I've shown here is that we have quite a bad recall. We have many false negatives, which means that actually most of the selections that we are seeing right now in humans, we did not predict it. And the assumptions that we've made for these predictions is that the fitness landscape was stable across mammals, meaning that the one we did not predict well is because this landscape has actually changed, probably. So these 35%, they are positive just because they are going back up toward fittest amino acids that were lost. So to take the analogy of what we saw this morning with the bicycle, it's like we have a rusty bicycle and you're just cleaning it. So you're beneficial in that way. While the other ones, the 65%, are beneficial because you adapt to a new environment.
Thank you.
Merci. Yes, sorry, do you have?
And have you looked into the variance in nomad and if you see also this nice calibration there with the new frequencies?
Sorry again? Yeah.
Have you looked into the variance in nomad and if you see also there this nice calibration with the frequencies, for example, into separating them in different groups?
No, I haven't.
For example, common variants, rare variants, super rare variants, singletons, and how it aligns with the scores you're
So, yeah, okay, so I haven't looked at nomads because here I looked at several. Actually, I show here in humans, but the data set I've used were across many populations where we didn't have that. But yeah, I completely agree that now that I've shown this in humans, I should focus more on actually what is available also in humans. Thank you.